Hello everyone. This is second lecture of week 2 of the course Process Equipment Design, and here we are going to discuss double pipe heat exchanger. Now if you remember, we have started this topic in last lecture, that is lecture 6th or first lecture of week 2. In that lecture we have discussed design steps about double pipe heat exchanger. Okay. And in this lecture we are going to illustrate the design of double pipe heat exchanger through an example. Okay. So, let us start with the example. Now, before starting that example, here I am having one table where property data of organic liquids are shown. Okay. Now, if you remember the last class or now, if you remember the last lecture, there we have discussed properties of different liquids or different fluids, right. So, in that property we have not discussed the density data, right. I have told you that you can find that data in Perry's handbook or similar handbooks also. So, in this slide I am showing the density data along with other data of the fluids. For example, if you see here we have this liquid, and corresponding to each liquid we have this density data. So, you can collect the density data from this table, and other data are also here. So, either you can collect the data from the graph which we have discussed in the last lecture, or you can directly collect that data from this table if that fluid is falling in this table, right. So, that is about the density data information. And from now we will start the example to design a double pipe heat exchanger. So, here I am considering example 1 where around 10,000 pound per hour of benzene will be heated up from 60 to 120 degree Fahrenheit by heat exchange with an aniline stream which is cooled from 150 to 100 degree Fahrenheit, right. So, number of 16 feet hairpins consists of 2-inch by 1.25 inch schedule 40 stainless steel pipe. So, I think you remember that what is the schedule number. If I am saying that 2-inch by 1.25, what is the meaning of that? 2-inch represents the outer diameter of the exchanger and 1.25 inch represents the inner diameter of the exchanger, right. What I can say, this is basically the nominal diameter of the equipment, or what I can say, this is basically the nominal diameter of the pipe, like 2-inch is the nominal diameter of outer pipe, 1.25 inch is the nominal diameter of inner pipe, right. And here I am having K value also, which represents the thermal conductivity of the material. As you can say, we have a stainless steel pipe. Fine. So, here we have benzene as well as aniline, one among that will flow in inner pipe and another will flow in annular pipe. So, we can see the combination of allocation of fluid to inner pipe or outer pipe, right. Now, if we further see, we can have maximum pressure drop of 20 psi, which is for both streams, right. So, we will calculate the pressure drop of each side and that should come lesser than 20 psi, fine. A specific gravity of benzene 0.879 and for aniline it is 1.022. So, you can get the density data from this problem only. And next we have to determine the number and configuration of hairpins that are required. Okay. So, here we are going to design the double pipe heat exchanger where we will fix the number of hairpins and the configuration. Configuration means whether it should be operated in series or parallel, right, that we have already discussed in the last lecture. So, let us start the solution of this problem. So, here we have to start with an assumption that the hairpins are connected in series on both sides, like I am considering the simplest configuration. Okay. So, if you remember, what we have to solve in this problem is we have to find the hairpins number as well as the configuration. So, first I am considering series configuration where both fluids are entering in series in double pipe heat exchanger. Okay. And for calculation purpose, we can consider that benzene is flowing in inner pipe and aniline is flowing in outer pipe, fine, and either fluid could be replaced in inner pipe. So, here we are considering first that benzene is flowing in inner pipe. If all design conditions will be satisfied, we will consider this configuration or consider this flow, otherwise we relocate the liquid to inner side or annular side, fine. And here we are considering that counter current movement between two fluids is occurring because we are considering series configuration. So, let us start with the solution of that with this assumption. So, what we have to compute first? We have to first collect the properties, and as you know that we have already discussed in the last lecture that property we usually collect at average temperature, fine. So, here fortunately for both fluids you know the terminal temperatures, inlet and outlet temperature of both fluids are known to you. So, you can simply calculate the average temperature and you can see the properties like viscosity, thermal conductivity and specific heat of two fluids, and all these information are available in the graph which we have discussed in the last class. I hope you understand how to collect the data from that graph, right. So, considering those figures, considering those figures, we can consider the viscosity, that is in centipoise, specific heat and thermal conductivity of benzene as well as for aniline. Along with that, you already know the density data, that is specific gravity of the fluids are known to you, right. So, considering these properties, we will first calculate the heat duty of the exchanger, fine. So, let us determine the heat duty, and further we will calculate the aniline flow rate, because here 10,000 pound per hour flow rate is given corresponding to benzene only. So, first of all we will make the heat duty and then balance the heat with the heat of another fluid to find out the flow rate of another fluid, right, because temperatures of both fluids are known to you, fine. So, to compute this we need the specific heat as a property which we have already collected. So, here I am having heat duty as Q, and that will be nothing but mCp delta T for benzene, B is representing for benzene. So, here you can simply make the balance, fine. So, 2,52,000 BTU per hour is the heat duty which should be balanced with the mCp dt of aniline, right, as A represents the aniline. So, when I am making the balance, I can find that 9692 pound per hour flow rate is available for aniline. So, if you compare the flow rates of two fluids, it is almost equal, right. So, once I am having the heat duty and flow rate of aniline, we will next calculate log mean temperature difference, and you understand here that I am considering counter current flow. So, you can simply calculate LMTD because that is a well known expression and you all know this expression being a chemical engineer. So, here I am having this LMTD which I have found as 34.76 Fahrenheit, and then we will further calculate heat transfer coefficient at inner pipe or at annular site, assuming psi I as 1. It means at present psi represents what? Psi represents the viscosity correction factor, fine. So, that I am considering 1 because right now I am not considering viscosity correction factor. That I will calculate further and then we will multiply that with the HI or HO, whatever we will obtain. Fine. Now, here we should also consider the diameter, because what you know the nominal diameter of outer pipe, that is 2 inches, and nominal diameter of inner pipe, that is 1.25 inches, right. So, we have to find out DI and DO. Fine. Now, if I am considering HI, what I have to focus on? I have to focus on DI value, so that I can collect from table B2. And what is that table B2? If you remember the last lecture, we have discussed the pipe information, fine, and that is corresponding to the nominal diameter, outer diameter and schedule number, if you remember, fine. So, here I am having for inner pipe nominal diameter as 1.25, schedule number 40, fine. So, let us discuss table B2. Now, if you focus on table B2, what is given over here? This is a part of table B2. Detail of this table we have already discussed in the last lecture. So, if you see, so here I am having 1.25 as a nominal diameter, if you remember the first column. Second column corresponds to the outer diameter, so that is 1.66. Now, what we have to find over here? We have to find out the inner diameter of inner pipe, fine, and that should corresponds to 40 schedule number, fine. So, 40 schedule number, if you see, it is available over here, and if you consider this fifth column, okay, that corresponds to inner dia, fine, and this is what? This is basically the thickness of pipe corresponds to 40 S, corresponds to 40 schedule number. So, here DI should be 1.38, fine. So, you see here I am already having 1.38 as inner dia, and that is in inches. So, we can convert that into feet and then we can calculate Reynolds number, fine. So, that is corresponding to the benzene. So, 10,000 pound per hour flow rate of benzene is given. Now, here we have this pi di mu. So, di is already you have calculated. So, di you have already calculated, and 0.55 is the viscosity of benzene, fine. If you refer the property table, and 2.419, this is basically the conversion, okay, because that viscosity is available in centipoise. So, considering these values, we can obtain Reynolds number as 83217, and it is falling under turbulent flow zone. Now, for turbulent flow zone, when I am having Reynolds number greater than 10 to the power 4, we can simply use Cedar-Tate equation, and this equation you can refer. And if I elaborate Nusselt's number, that would be HI di by K. So, simply you can calculate, considering this equation, the heat transfer coefficient value, and that comes as 290 BTU per hour feet square degree Fahrenheit. Okay. Prandtl number you can calculate because you already know the properties. Now, here what we have considered? We have considered the heat transfer coefficient value without viscosity correction factor, fine, because I am not focusing on psi value right now, that I have assumed as 1. So, here I am having the value of HI. Next is, now further we have to find out heat transfer coefficient in annular side, right, where aniline is moving, fine. So, to calculate that HO, we are further assuming phi not equal to 1, because I am not considering viscosity correction factor, and further we have to find out D2 and D1, fine. So, how I can find these values? These should be corresponding to 2 inches and 1.25 inches nominal diameters, if you remember, fine, because in annular side we have to consider equivalent diameter, not di or d naught. So, for that purpose we have to calculate. So, for that purpose we have to calculate the di and d naught. Now, what is di over here? Di, if I am considering double pipe heat exchanger, di is what? Di is the outer diameter of inner pipe, right, and d naught or do will be what? That will be the inner diameter of outer pipe. I hope you are understanding. So, let us collect that values from the table B2. So, again I am considering this table B2, the part of table B2. So, if you see we have 1.25, okay, and what I have told you that di corresponds to the outer diameter of inner pipe. So, inner pipe nominal diameter is 1.25 and this is the outer diameter of 1.25 nominal diameter pipe, right. And for 2 inches we have to consider the inner diameter corresponds to 40 schedule number. So, if you see value should come as 2.067. I hope you can understand that. So, corresponding to this we can have di and d2 value, and we have just seen how these values have been obtained. Now, once I am having d2 and di, now once I am having d2 and d1, which I have also represented as d naught and di corresponding to annular side, not di of inner pipe, right, which we have discussed in the last slide. So, here we have d2 and d1 value, and considering this we can calculate equivalent diameter as 0.0339 feet, fine. And next we can find out the flow area pi by 4 d2 square minus d1 square, that is simple calculation. So, you can find this value, and further we can find out the Reynolds number in annular side, right. So, this equivalent diameter we have, so this equivalent diameter we just have calculated, and considering mass flow rate of aniline and viscosity of aniline with the conversion factor, we can find out Reynolds number as 8212. So, if you see this range of Reynolds number, the flow is transition flow, okay. So, that should be, so if I am having the transition flow, we have to use another equation which is shown over here, okay. So, you can consider this equation, okay. This is basically the Hausen equation if you remember the last lecture, and here I can find out H naught corresponding to thermal conductivity of aniline and equivalent diameter. So, this is the whole expression, and when you put the values over here, thermal conductivity and Reynolds number, Prandtl number value, fine. So, corresponding to all these value you can find out HO value as 283 BTU per hour feet square degree Fahrenheit. So, in this way you can calculate HI and H naught, and now we will focus on the psi values where I have to focus on viscosity correction factors, right. Now, how to calculate viscosity correction factor? Viscosity correction factor, if you remember, that is basically mu by mu w, and mu w is what? Mu w is basically the viscosity of the fluid at wall temperature, okay, and mu is the viscosity of the fluid at average temperature, which we already having in a property table, fine. So, let us first consider the wall temperature, how to calculate that. So, this is the expression for wall temperature, and T average and this capital T average, these values of temperature of both fluids are known to us. So, we can simply calculate that. HI and H naught we have already calculated. So, considering all these values, we can find out wall temperature as 108.9 degree Fahrenheit, okay. Now, corresponding to the figures of what? Figures of viscosity data, fine. We can find out benzene viscosity and aniline viscosity at 108.9 degree Fahrenheit, and it comes out as mu b as 0.47 centipoise, and here P should be capital, sorry for that. P should be capital. Fine. So, here mu B is 0.47 centipoise and mu A is 2.4 centipoise. Okay. Considering these values of viscosity at wall temperature and viscosity at average temperature of both fluids, we can find out viscosity correction factors like this, where psi I is equal to 1.0222 and psi naught is equal to 0.9748. Fine. So, considering these value, we can calculate H I and H naught as 296 BTU/R feet square degree Fahrenheit and 276 BTU/R feet square degree Fahrenheit respectively. So, in this way you can find out H I and H naught with viscosity correction factor. Now, once you are having this H I and H naught, what we have to calculate first? Obviously, the overall heat transfer coefficient. Fine. So, if you remember the overall heat transfer coefficient expressions, it includes 5 terms, in which 2 terms corresponding to dirt factor of both fluids. Fine. So, in this case, both fluids like benzene and aniline, these fluids fall in organic liquid range. Fine. So, in both fluids we can consider same dirt factor, okay, because both are falling in same category. So, for that purpose we have considered dirt factor as 0.001 R feet square degree Fahrenheit per BTU. Okay. So, this is for both fluids. Considering this, we can calculate overall heat transfer coefficient using this expression, where RDI and RD naught are dirt factor value, and in some expressions we can use dirt coefficient, that would be HOD or HID if you remember the basic design parameters lecture, right. So, considering DI D naught, HI H naught and thermal conductivity of the material, that is already given in the problem. So, considering all these value, we can find out overall heat transfer coefficient at dirt condition as 89 BTU per hour feet square degree Fahrenheit. So, here you can calculate overall heat transfer coefficient, and next what we have to find out, we already have calculated the heat duty, overall heat transfer coefficient, and LMTD is already with me. So, what we have to calculate next is the heat transfer area. Fine. So, this is very common equation for heat transfer area, that is the duty should be equal to UA delta T mean, and that should be LM. Here it is not IN, it should be LN, that is the log mean temperature difference. Fine. So, considering all these value, we can find out area as 81.5 feet square. And next what we have to find out? We have to find out the overall length of the exchanger, okay, because we have to calculate the hairpins, and one hairpins, one side of that is 16 feet. Fine. So, we will first calculate the overall length, and then we will find the hairpins number by dividing that value with the length of one hairpin. Okay. So, let us focus on the calculation of total length of the exchanger, and to calculate that we need the external surface area per foot of inner pipe, that is 1.25 inch schedule 40 pipe. Okay. And that value comes as 0.435. So, how I can obtain that value? That value I can extract from this table, which is a part of table B2. Now, here I am having 1.25 nominal diameter pipe, and if you see here we have the, if you see the table B2 properly, at the top we have different column names, okay, and this column corresponds to the surface area per unit length. Okay. So, correspond to 40 schedule number, we can find out value as 4.435. Okay. So, 435 feet square per unit length. fine. So, total heat transfer area I already know, and I will consider this 0.435 as a perimeter. So, you can consider 187.4 feet is the total length of double pipe heat exchanger. Okay. And further, if I am considering 16 feet hairpin, so total length of the pipe is 32 feet, right. Now, if you remember the last lecture, in that lecture I have told you that hairpin length is 16 feet, so that is the total length, but that is given as half of the length, right. So, if I am saying 8 feet hairpin or 16 feet hairpin, it means it is only the half length of the total pipe, fine. So, if I am having 16 feet, 32 feet is the total length, and 187.4 feet length we have already seen as a total length of exchanger. So, we can simply find out 6 hairpins as total number of hairpins, right, in this example. Now, further we will focus on pressure drop calculations. So, first of all we should focus on pressure drop of inner pipe where benzene stream is available. Okay. So, for that purpose we can calculate the frictional factor first. So, that expression we have already discussed in the last lecture. So, corresponding to the Reynolds number you can choose the F factor. So, in this case Reynolds number is 83,217 and other parameters are not required. So, we can simply calculate friction factor over here. We can simply calculate friction factor over here, and the flow area we can find out, and division of mass flow rate divided by flow area will give the capital G value, that mass flow rate per unit area, right. So, value comes as this value. Now, the pressure drop in straight section of the pipe is calculated using following equation. Now, if you remember the pressure drop discussion, calculation which we have discussed in the last lecture, in double pipe heat exchanger we have two sections. First is the straight pipe where flow is occurring in a straight pipe, and second is the band, okay, return band. So, we can consider pressure drop in two sections simultaneously, and then we add those pressure drops to find out total pressure drop in double pipe heat exchanger in inner side or in annular side, right. So, this is the expression to calculate pressure drop in inner pipe, and considering all these values where this S corresponds to the specific heat of the, specific gravity of the benzene, fine. So, that value you already can see from the problem, and putting all these values we can consider pressure drop as 6.1 psi, that is in a straight pipe only. Now, pressure drop in a return pipe or in return band, we can consider this expression because it will depend on the number of hairpins that we have computed as 6. You know all other parameters and you can simply find out pressure drop in return pipe as 1.85 psi, okay, and addition of this two will give the total pressure drop in inner pipe, right. So, here I am having total pressure drop as 8 psi. So, if you recall the limit of pressure drop, that is 20 psi should be the maximum limit, okay, but here I am getting 8. So, here I am working in safer side, right. So, now calculate the pressure drop of aniline which is flowing in annular side, fine. So, here we have the expression corresponding to the Reynolds number. So, you can find that value of F like this, okay, and further we can calculate the flow area, okay. So, if you recall the last slide, there we can obtain the flow area, and that flow area you can simply find out through table B2, fine. So, all these values are given, okay. So, here I am having the flow area, and corresponding to this G value you can obtain like this, and further we can find out the pressure drop in straight pipe and pressure drop in return pipe. So, we will first calculate the pressure drop in straight pipe. So, you have all values including the specific gravity of aniline and including the annular and including the equivalent diameter, right. So, pressure drop in a straight pipe you can find out as 47.5 psi, fine. So, here you should not calculate the pressure drop in return band, because this pressure drop is already exceeding then the permissible limit, which is 20 psi, fine. So, here my design becomes infeasible. We have to design in such a way so that both pressure drops should lie within 20 psi. Okay. So, here we have to start the second trial, okay. But what we can summarize from this first trial is the pressure drop and annular side is too large, that we have already seen, and Reynolds number in annulus is less than 10,000. So, flow in annular side or flow in annulus is in transition zone, which we should not use. Okay. So, what we can do to overcome this, that we have two possibilities. First is we can switch the fluids, okay, and second is we can connect the annuli in parallel, fine, because what we have to do over here, we are not focusing on inner size, because there already we are in a safer side, right. But in annular side or annulus or annuli, we can consider lesser pressure drop, and therefore, we will divide the flow in annular side only, not in inner pipe. Okay. And these two possibility I have already discussed in lecture 1 also, because what we should do when the infeasibility occur. So, these two options we have already focused there also. Okay. So, effect of these two possibility changes on Reynolds number and pressure drop can be estimated as, first of all, if I am switching the fluid. Okay. So, what will happen? Since the flow rates of two streams are approximately the same, okay, because both fluids are more or less 10,000, one is 10,000 and second is 9697, something like that. So, both of the fluids are in same flow. Okay. So, Reynolds number will definitely be the function of viscosity over here, okay, and that should be inversely proportional to, fine. So, considering this, we can simply switch the fluid, that aniline is flowing in inner pipe and benzene is flowing in outer pipe. So, if I am considering that reverse of Reynolds number or switching of Reynolds number, we can find these Reynolds number in inner pipe and annular side. It means both are falling in turbulent zone, fine. So, once I am having the Reynolds number of two side, we can calculate the pressure drop of two side. So, pressure drop changes we can further find out based on specific gravity value. Okay. So, Reynolds number, so pressure drop of annular side for straight pipe 6.1 we have obtained, and this is the switching of Reynolds number. So, here we can find out final Reynolds number as 7 psi in inner pipe and 41 psi in annulus side. Okay. So, here again it is more than 20 psi. So, obviously switching the fluid does not solve my problem, as it is not reducing annulus side pressure drop, fine. So, we have to connect. So, we have to go for the second option, and that is to connect the annuli in two parallel banks. Okay. So, in this case what will happen, because whatever would be the Reynolds number, it is divided in two section, because we are considering the parallel flow, right. So, here I am having the Reynolds number like this, which we have divided by 2. So, 41 100 Reynolds number is in annular side, and you see further, and you see the revised pressure drop in annular side we can obtain as 7 psi. So, apparently this modification will take care of the pressure drop, but will push the Reynolds number further into the transition region, because now the Reynolds number is less than 10,000. Fine. So, what we can consider, switching the fluid and changing the pattern. Changing the pattern means changing the configuration is not solving my problem. Okay. Though it is falling under a required pressure drop, but it is putting the liquid to the transition zone, which we should avoid. So, what we can consider? We can consider the combination of two options together. So, considering this, we can make a third alternative where switching as well as connect the annuli in two parallel bank, both we should consider. So, here I am having the Reynolds number. Now, if you remember, this value was 30,000 when I have considered switching of the fluid, but because of the parallel flow, this value becomes half. Okay. Considering this, we can find out the pressure drop. So, that comes as 7 psi, right. So, it appears that this alternative will meet all design requirement. However, we have to carry out sufficient calculation to find out Hi and H naught further and mean temperature difference, because all configurations are changing, and we also have to see the effect of that on hairpin number. So, let us consider the another trial, which I am saying as second trial, because here I am calculating, here I am revising all calculations for second time. Okay. So, here I am having benzene in annulus side and aniline in inner pipe. So, here I am having the temperature differences, and because I am considering parallel flow, I have to calculate Ft factor also, and that we can consider depending upon the branches. So, we can consider two branches over here. So, Ft value we can obtain as 0.836. Considering this, we can calculate Hi value and H naught value like this. I am not going into detail of that, because this we have already discussed in first trial. We can calculate the wall temperature and then the viscosity correction factor and then the revised Hi and H naught value, and so the dirt factor, and so the overall heat transfer coefficient considering dirt factor, right. And then we will further calculate the total length, how much total length will be required. So, that comes out as 289, and this is corresponding to the previous calculation only. So, I am not going into detail of this. If you consider the hairpin, that comes as 9. Okay. So, 9 hairpins are odd number. However, the equation for LMTD correction factor is based on assumption that both parallel branches are identical, and therefore, we use 2 branches for 5 hairpins or 2 banks of 5 hairpins. So, total number of hairpins will be 10. Okay. So, considering this, we can calculate the pressure drop for inner side. So, it comes as 11.9 psi, and for reverse side or the return band, we can consider pressure drop as 2.6. So, total pressure drop in inner pipe is 14.5, and similarly we can find out the pressure drop in annular side, and that should be 11.6. So, both pressure drop are falling in a range. Now, finally, we have to find out that how much over design we are considering. So, that we have to calculate overall heat. So, for that we have to calculate area for clean condition and for dirt condition. Okay. So, you can calculate overall heat transfer coefficient at clean condition, and area you can obtain as 107 feet square, right. And for 10 hairpin of 20 and for 10 hairpins of 32 length, you can find out area as 139 feet square. Comparing these two will give the oversize as 10.6%. So, this much is the oversize. We have considered all feasibility and we met all design in the feasible limit. Okay. So, that is all about example 1 and that is all about this lecture. So, that is all for now. Thank you.